Hi, I'm Bruce, and welcome once again to my Colorado Rocky Mountain Lab. And today I've got a little something different. It's a project instead of a piece of equipment for sale. And what I'm doing is experimenting with something called a ratio transformer. These kind of devices they're still around, but they were used quite commonly in the 50s and 60s. Um, Ratio transformers are special toroidally tapped transformers. They tapped at 10 positions generally. And then there's, in this particular unit right here, which it's a Gertsch ratio transformer, but it was apparently licensed under Singer. And there are five transformers inside of there, each tapped 10 positions. And they're really an interesting item because whatever you put in AC wise, as long as you are within the frequency and voltage range that is established for it on the front plate, you can dial and divide down that incoming voltage in a fashion that's similar to a Kelvin Riley divider, if you're familiar with that thing. Um, where the Kelvin Riley is mostly used in DC. This is an AC analog to it. It produces decades of voltage, um, starting with your ones and working your way down to, in this case, the 10 millionths. And often I found that they are involved in AC calibration devices. And generally, in an AC calibration unit, you've got a couple of major components. You've got, first of all, a signal source. You want that signal source to be stable, um, primarily. And it's nice if you can have variable frequency, which I do on this, and it's low harmonic distortion. This is a low harmonic distortion signal source that I built intending to use for analyzing harmonic distortion on amplifiers, but in this case it's going to work just fine to provide my base signal for this calibration unit. Now I'm running that signal into a multi-pot unit where I've got roughly 10,000 ohms across the output of this harmonic distortion source, and then I'm using a pot to tap off the voltage that I want to give me some calibration. These are 20 turn pots. I want some room to calibrate and be able to make fine adjustments. So I've got a coarse adjustment here with a 20 turn 10K pot, and I've got 20 turn 100 ohm pot down below for my fine adjustment. And then the signal that comes out of that goes into my amplifier here, which in this case it's a Hewlett Packard 465A, which has a frequency response, I think 2 dB from 5 to about a megahertz, and then it's very flat from like 100 hertz up to I don't know, 10 kilohertz, something like that. I don't remember the exact spec, but I'm thinking it was within a half a dB, maybe better. Um, but anyway, I'm amplifying up that signal that comes from my low distortion source, which has been voltage adjusted here. I adjust it so that the output of that amplifier provides what I need 10 volt wise to go into this Gertsch ratio transformer. And once I've got 10 volts going in, then I have it set so that I'm reading in decades what my voltage will be. Now let me demonstrate what I mean by that. All right now we're at 9.9994 and we're fluctuating in the 100 millionths. I'm going to adjust that 100 millionths to try and get me just a little closer. Right about there. All right, and then I'm going to turn my second dial down. I'll leave the first one at 9, but right now we're reading 99999, and we are getting 10 on the meter, which if you were one digit off, you would be getting all nines. So let me turn the second digit down. Here goes. Now we're reading 98, but then 999. If I go the next one and I go say 7, now we got 987 with two nines after, which fluctuates between 988 and 987. We got 79. Let's go 6 on the 9. 9876. And then we have 9 at the end. Let's take that 9 at the end down to 5. 986, 98765 with a little fluctuation. So let's ignore the 10 million spot and take a look at that millivolt area there. I've got 9.876 volts right to the millivolt that I dialed in using this unit. Now, can you do that with anything on your bench? Can you provide 9.876 volts of AC? Now, this is at 100 hertz. I'm going to change to 1,000 hertz. We're going to go back up to our full scale here on the Gertsch. And we're going to once again adjust our voltage for 10. All right, we're going to call that 10. Let's go 9, 8, 7, 6, 5. 9876, and again, negating the 10 million spot, we're right there. I could touch that up just a hair. So it's a pretty amazing unit. Now let's take it 9 to an 8. So we're 8, 8, 7, 6, 8, 7, 7, 6. We can raise this up just a hair just so we get a little easier to read. Agreement. 7, 7, 7, 6, 6, 7, 7, 6. So you're getting the idea. It's pretty amazing. Okay, we got 6, 7, 5, 6. 5, 5, 5, 5. There's all fives. So that's an example of what you can do with one of these ratio transformers. Now I could use that voltage, that calibrated AC voltage. I've chosen 1 kilohertz. I had 100 kilohertz. I could throw 10 on here, but I have to be careful that I don't overdo the plate value of input voltage. So yeah, according to the front plate, my maximum frequency has to be such that 0.35 times my frequency must be less than or equal to 350 as a number, and that turns out to be volts that they're discussing. So another way of looking at that would be to say 350 volts over 0.35, and that would give me 1,000. Now, if I wanted to go beyond 1,000, let's say I want to go up to 10,000. That's a factor of 10 times more. That means my voltage, my 350 volts, has to be reduced by a factor of 10. So we get on to 35. I'm working with 0 to 10 here, so it doesn't matter to me. At 10,000 hertz, I'd be good at 10 volts. It's less than a third of a 35 volt maximum. Anyway, that's one of the disclaimers and things you have to worry about on the ratio transformer. The frequency range most often used for maximum accuracy is under 3,000 hertz, say from 60 to 3,000. You can use it up to 10,000, but at a reduced accuracy. It's not a heavily reduced accuracy, maybe a decade, so you're working around 0.01, something like that percent. Still pretty amazing. And this particular unit also has two inputs. I've got like an I input, I think it says, and the other says a center tap or CT input. If I was to go into the center tap, I'm taking the voltage that I'm bringing in and I'm doubling it. So I put a 5 volt in, I get a 10 volt signal through the ratio transformer. I believe it is at a slightly reduced precision doing that, so I'm running into the I terminal. All right, let's carry on. The stated accuracy for these units is about 0.001%, so a thousandth of a percent. Pretty amazing precision. And as long as you leave it basically unloaded, so you're using a high impedance on the output, and it doesn't load it down and create currents through the transformers, then you're going to have a very accurate output as a proportion to the input. We are still at 5.555 right now, with small fluctuations in the 10 millionths or 100 millionths place. So there we go. If I was to change my amplifier to 40 dB instead of 20, so I get a gain of 100 instead of 20, I would wind up kicking my signal source way up into the range above the saturation of that amplifier. So you have to make sure that you've got enough swing in your amplifier to be able to take those AC peaks. In this case, I've got no problem, up to about 20 volts, I think, on this unit. So there you go. There's a little introduction to a ratio transformer. Usefulness. What are they used for? They're used for calibrating meters, providing AC calibration voltages for use in oscilloscopes or anything. You could use it on the input of an amplifier that you want to test. You provide a very known input down to a thousandth of a volt, and then you can calculate your gain, for instance, to within, say a gain of 1,000, and still maintain really high percentage of accuracy. Anywhere that you need a calibrated AC voltage, so you think it up. Bridge circuits would be another one. Okay. Thank you for listening, and I hope you learned just a little something about the ratio transformer.